Okay, so here we're going to start talking about applications of the antiderivative. So we've discussed the antiderivative, which we also call the indefinite integral. And this big application of an antiderivative that we're going to discuss here is really the definition of a definite integral. And so to get started, we need to talk about summation notation or sigma notation. And sigma notation essentially would be this symbol right here, which is summation notation. And what it tells us is we're going to add a bunch of things together. So if we have a bunch of terms, A1, A2, A3, all the way up to say AN, and we want to add them together, we can do it this way. So we can take the sum, which is this symbol right here, of A sub I, where I, which is our index, I is the index, starts at 1 and goes up to N. And so that means we're going to plug 1 in for I, then 2 in for I, then 3 in for I, which would give us A sub 1, A sub 2, A sub 3, all the way up till we get to this top number right here, which is N in this case, and that would be the last one we go to, A sub N. So I is the index, the lower bound is 1, the upper bound is N, and we're going to add all those values up, which is what this symbol tells us to do. So that's just a notation for adding a bunch of terms together. We're not going to get too deep into that because we don't need to right now, but we can really talk about how summation notation works more specifically. We can talk about ways of adding certain terms together without actually sitting there and adding all these terms together. But we're not really going to need to get into that. So this is the most typical way of describing the application that we're going to discuss. It just says use rectangles to find an approximation of the area of the region lying between the graph of 1 minus x squared, the x-axis between x equals 0 and x equals 1. So if we're going to draw that, this curve right here would be the 1 minus x squared. And you should know this. It's going to be up 1 unit. It's minus x squared, so it's a flipped over parabola. The x-axis is one of the bounds, and it's between x equals 0, which is the y-axis, and x equals 1 would be right here where it hits the x-axis. So the space that we're trying to find the area of is this space in here. Now, in order to do that, we want to do it through approximations. Now, one major problem with trying to find that area is it's a curve. I mean, this side right here is curved. So it's not very easy for us to calculate that area using some basic geometric formulas. But what we could do is we can approximate that area with rectangles. Now we use rectangles simply because the area of a rectangle is extremely easy to compute. We could use other geometric figures and try and fit them in there. I mean, if you want to get crazy with it, we could put trapezoids or triangles or circles. You know, the idea is I can take a bunch of circles and try and fill this space up with circles and try and use that to approximate the area. I'm not going to do that. That's not beneficial to us. So we're going to use rectangles. So the idea with these rectangles is that we're going to take a certain amount. It doesn't really matter how many you start with. Sometimes the problem will specify how many you start with. In the long run, we're going to have a much better way of doing this whole thing. This is just an introduction. So let's say we wanted to use 4 rectangles to compute this area. So the idea here is if I take these 4 rectangles, I'd have to take this interval right here, and I'd have to subdivide it into 4 parts. Now the way I can do that is I can take the starting point, which is 0, the ending point, which is 1, and take that total distance and divide it by the number of subdivisions I want, in this case 4. So the total distance would be 1 minus 0, so 1, divided by, I want 4 rectangles, so divided by 4, so I would get 1/4. So that means each width of these rectangles would be 1/4. So this would be 1/4, this would be 2/4, so a half, this would be 3/4, and that'd be 1. But that would make the width of each one of these rectangles exactly the same. Now they don't have to be the same, but for computation purposes, it's much easier if they are. All right, so then what we want to do is we want to get the height of the rectangle. There's a couple ways we can do this. This picture shows the height of the rectangle where the left-hand edge of this interval or this width of this rectangle goes up to the function and hits the function to get my height. And so I make my rectangle right there, and now the left-hand side of this one goes up to the function to get my height of that rectangle. Same thing here, same thing here. What that creates, because this function is decreasing like this, it's creating all my rectangles peeking outside of my area. So this, they're all above the curve. So if I took this area, area 1 plus area 2 plus area 3 plus area 4, and added those three areas together, that would give me an idea or an approximation of the area I'm trying to find, which is ultimately this area right here. The problem is I would be an overestimate. It's an overestimate because I have too much. Okay? If you look at how much extra I have, all this extra space out here is more than what I need. But an overestimate is an estimate nonetheless, and I could, compute that. So then I could say, all right, well, let's now switch that to more rectangles. So if I want to put more rectangles in it, here I have 1, 2, 3, 4, 5, 6, 7, 8. So I doubled the size of the number of rectangles I want, and I can compute that area. How would I figure out how wide each rectangle is? The width of the rectangle will be the total distance. If I start at 0 and I end at 1, take the total distance, and this time I'm going to divide by 8. So 1/8 would be the width of each rectangle. So this one would be 1/8. This one would be 2/8, which would be 1/4. And then we keep going, 3/8, etc. Right? But the width in each one of these is going to be 1/8. So if you look, every time I want to find the width of my rectangle, I take the total distance, which is the two endpoints, the difference between them, divided by the number of subdivisions. So we call this width of this rectangles delta x. And we take, if we call this a and we call this b, we do b minus a over n. B minus a are the endpoints, n is the number of subdivisions. Okay? And that'll always tell me how wide each rectangle needs to be. All right, but anyway, back to this picture. If you look at this picture here, and I make the left-hand side of every rectangle go up and hit the function, and that's how I get my height. The left-hand side hits the function, that's how I get my height. Left-hand side gets the function, etc. And that's how I get all my heights. Look at now how much my rectangles are over the curve. I have all this red space here is my overestimate again. But that overestimate is less than this one, because if you think about this, if I go back to this picture over here, and this is starting to get a little busy, but if I go back to this picture here, let me use a different color. The subdivision was split in half, right? So now I have twice as many. So if the left-hand side of this rectangle hits the curve, and then that's my height, and the left-hand side of this rectangle hits the curve, and I keep doing that, if you look, this is how much I'm over by. This space here, which is less than what this space was originally. So I'm reducing the amount I'm overestimating by every time I put more rectangles into the picture. I can get more rectangles in the picture. In this case now, the number of subdivisions would be 16, so I'm doubling it again. And to the point where if I keep doing this, I'm going to let the number of subdivisions, which is n, go to infinity. Eventually, the overestimate will be so small that I'll get really close, if not exactly, to my area. Okay. Now, there's another way I could do this, and the other way I could do this, I'm going to start from scratch here, erase this, would to not be an overestimate, but to be an underestimate. So the way I do that is if I made the right-hand side of every rectangle hit the function to get the height of my rectangle. And this hits the function, that's the height of my rectangle. This hits the function, that's the height of my rectangle. And then here, it's at the x-axis, so the height of the rectangle would be 0 here. So this is now the area that I'm computing. And you could say here, this is the fourth rectangle. So you can still say I have 4 rectangles. This one just doesn't have any height to it. And so now if you look, I'm off by this amount, but now I'm under what the actual area should be. And that would be an underestimate. And I could keep doing that with 8 rectangles and 16 rectangles. The only difference is that would be an underestimate versus an overestimate. Ultimately, it really doesn't matter, because if you look, either way, if the number of rectangles increases and goes to infinity, right, the estimate is getting closer and closer to the actual area. The amount I'm over by or the amount I'm under by starts to get smaller and smaller to the point where they're both approaching the actual area. So an overestimate versus underestimate really is irrelevant. You could pick either one. Now, to do this in practice is not easy. To do the computation to get this, you're going to have to do some work with summations. So the way we do this with summations, if you think about what are we adding up? Well, what we're adding up are the areas of the rectangles, area 1, 2, 3, 4, 5, etc. Now, the area of rectangle is based off of width and height. No matter how we compute the height, whether it's the left-hand side of the rectangle, the right-hand side of the rectangle, I could even use the middle of the rectangle to hit the function. Whatever it is, the height of the rectangle is based off of some part of the rectangle going to the function, and when you hit the function, that's your height. That's your y value. So the function value is your height. So the idea is the width, we said we can compute using this delta x. And the height is some function value, f of c sub I, somewhere in the interval where I got my width. Again, is it the right-hand side of the rectangle and that's it? Is it the left-hand side? And I can keep alternating. If you look at this picture, sometimes the left-hand side of the rectangle hits the function, sometimes the right. So in this case, because this function switches from increasing to decreasing to increasing, they always wanted to get an overestimate. And if they always wanted to get an overestimate, they always made a different part of the rectangle hit the function so that the rectangles were always peaking above the curve. Again, conceptually, that's not that hard to understand. I think computationally, it's very difficult to do. But anyway, we're going to add a bunch of rectangles together. And this is the area of each rectangle. So this would be the area of rectangle 1, the area of rectangle 2. Again, this is my height, and this is my width. And I'm going to do it for a certain amount of rectangles. So let's say I'm going to do it for n rectangles. So I want my index to go from one rectangle, the first rectangle, to the nth rectangle. And so that way I can say, all right, well, if I want 5 or 6 or 7, I just have to change this number. And I could do it again. I could do it with an underestimate too. It all depends on how I compute the function value. Is the function value computed by using the left-hand side of the rectangle or the right-hand side of the rectangle? Again, we don't have to get into that detail all so much. What we do want to do is just talk about, general concept. And so when you look at these two pictures, this one is an overestimate, this one's an underestimate. If I added these rectangles up, I'd be over what the area I'm looking for is bounded under the curve. This would be an underestimate because all the rectangles are sitting below this curve over this interval. Okay, and again, remember that delta x is always b minus a over n. And I do that for a specific reason, b minus a. B is always the bigger number of the two. And if I always take my bigger minus my smaller, this value is always positive. And then if that's always positive, n is the number of subdivisions, so the number of rectangles you want, that's always going to be positive. You never want a negative amount of rectangles. So that makes sure that my width is always going to be a positive value. All right, just some terminology real quick. The rectangles we're talking about here can be either circumscribed or inscribed. Circumscribed rectangles are ones that are above the curve like that. We call that an upper sum. Inscribed rectangles are the ones that are below the curve like this, and that's what we call the lower sum. So this is my overestimate, this is my underestimate. Again, which one you have doesn't matter because we saw in the last slide that the more rectangles you put into this picture, the smaller your error will be, the smaller your overestimate or underestimate will be towards the actual area you're looking for. And so we just need to talk about this summation here. This is the summation that will add a certain number of rectangles together. Okay, so now the whole trick to getting this to go from an estimate to the actual area is to then use a limit. So we talked about just a second ago that this right here is the notation we would use to tell us that we're going to add a certain amount of rectangles together. Height here and width, that's right there in the middle. This is telling me we're going to add them up for n rectangles. Now, again, a second ago I said, if we get 4 rectangles and then 8 rectangles and then 16 rectangles and then 1,000 rectangles, what we're doing is we're slowly getting closer and closer to the actual area we're trying to compute. Each one will be an estimate, but we're getting closer and closer and closer to the actual area. So what we're doing is we're letting the number of rectangles get closer and closer to infinity. And so as it gets closer to infinity, we get closer to the area. So if we then take the limit as n goes to infinity of this summation, of this rectangle, what that does is it takes this estimate and it makes that estimate better and better to the point where we actually end up getting this actual area. So this right here is a way of computing the area bounded by a curve and the x-axis between two vertical lines. So if I took any curve, okay, here, no matter what that curve is, above the x-axis, bounded on one side by the x-axis between these two vertical lines, A and B, and I want to find the area in between, that's what this would be doing. Again, in practice, how do you actually work that computation out? It would take us quite a bit of time to get you comfortable with that, but it's not really necessary. Notice there's one part to this definition of the area of the region, and that definition looks at the fact that the function is continuous and non-negative. So the function being continuous and non-negative is important. That means this function here is all one solid piece. That's a pretty critical thing. If there are breaks in this graph, we have major issues with doing this. And non-negative. Non-negative means that this function is above the x-axis. One reason for that is simply because of the way we compute the heights of our rectangles. The heights of our rectangles are based off of some function value. So it's either the function value on the left-hand side or the right-hand side, but it's some function value, some f of x value. Well, if we're above the x-axis, that y value or that f of x value would be positive. And so we already said delta x will be positive, and if this is positive, positive times a positive would give me a positive. So the area of that rectangle that we're then adding up would be a positive area. However, if your function were below the x-axis and we wanted to find this area, and we use the function value here for that, while we could add up all these rectangles the same using this formula, we could add it. There would be no problem to add all these rectangles up using this formula. We would get a negative answer because we'd have a positive width for every single one of these, but the heights would be based off of the y values down here, which would be negative. So you'd have a negative times a positive to give you this area and this area and this area. So overall, each rectangle's area would be negative. And if you add a bunch of negative values together, even if the number of them goes to infinity, you would get a negative answer. But that can't be area. So if you truly want this formula to represent area, we have to talk about adding a bunch of non-negative values together. All right. That's only as it relates to this area. Now there's a quick trick to fix that, is if I just take all these y values down here and I flip them up to here and I make it look like that, that area should be the same as this area, but now the y values are positive. So if I simply take, this is starting to get a little overwhelming, if I simply take this y value and I multiply it by a negative, it would now be a positive y value, and it would be up here. The distance from here to here would still be the same as the distance from here to here, but now it's based off of a positive y instead of a negative y. And then now my area would be sufficient. So there's a way around it if it's not negative. You just have to make that correction. But overall, right now, what I want you to focus on is that if I looked at this summation, what do the parts of this summation mean? What this says, I'm adding up a bunch of rectangles. This is my height. This is my width. And if I let the limit as n goes to infinity of that summation, then what that can do is that could give me the area of the space bounded by a curve, the x-axis, between two vertical values. This then brings us to the definition of a definite integral. Again, we've had indefinite integrals. Indefinite integrals look like this, where we take the integral of some function dx and we get the antiderivative plus c. Okay? Now, what we just talked about a second ago, which was this limit as the sum of f of c sub I times delta x sub I, that right there is what we call the definition of this. This is a definite integral. Now, the difference between a definite integral and an indefinite integral, notation-wise, doesn't look like there's very much difference. The difference here is that I have this little a and b here. But what they mean is something very, very different. This right here just said, let's find the antiderivative. Let's find the antiderivative. Let's go backwards on the derivative formulas and find the antiderivative, and that's it. What this is saying is that this definite integral, right, which again looks very much like this indefinite integral, this definite integral means this, okay, where it's equal to that, which is the limit as n goes to infinity of this summation of f of c sub I times delta x. Now, that seems like a very drastic difference for something that really should be somewhat similar. Well, we're almost to the point where showing how these two relate to one another. But we know what this means, and this is essentially talking about adding up a bunch of rectangles, areas, and letting the number of those rectangles go to infinity. A couple of things here. This a to b here that's on this integration, that a to b is the same as the a to b that was the interval that we were working with for the area, the a to b. That distance, it's the distance along the x-axis. It's an interval on the x-axis. That's the same a to b that's here that we were working with before when we were doing this just a second ago. A is called the lower limit of integration, and b is the upper limit of integration. And so if I want to compute the integral of 2x dx, that would be x squared plus c. And that's an indefinite integral. This says if I want to do the integral from 0 to 1 of 2x dx, I would have to do this, which is a drastic difference. We haven't even talked about how this actually comes about. I mean, if you really want to think about this as a picture, think about what 2x looks like. 2x is just this line with a slope of 2. Here's 0, here's 1, and here's the x-axis. So essentially what I'm talking about is finding this area. Now this is a triangle, so I could find that area very simply by doing 1/2 base times height. Base would be 1, height would be 2 since this is 2x. And if I did 1/2 base times height, it would be 1/2 times 1 times 2, which would give me 1. But the idea is the way we're computing this and the way we're computing this seem to be very different right now. All right. Almost to the point where we show how these two things are related, because they're both integrals. This is an indefinite integral. This is what we call a definite integral. Why would we use things so similar to one another but do them so differently? Well, that's because there's one more thing we need to talk about that'll start to link this together. So this is it. This is the link between the differential calculus and the integral calculus. So we've really talked about the two different branches of calc. Differential calculus is all the stuff we talked about as it relates to derivatives. So we've talked about derivatives, we've talked about how to find the derivative, we've talked about applications of derivatives, and then we're going to talk about integral calculus. Well, we've already done that. So one part of integral calculus is to talk about the antiderivative. In some ways you might think that that's still differential calculus because we're just going backwards, and it really is. That's still differential vein. And then we've talked about the idea of integral calculus as the idea of calculating those areas with a definite integral. And again, they seem like they're very, very different things. But here's where they come together. The Fundamental Theorem of Calculus, which sounds like it's a big, serious theorem, and it is. The Fundamental Theorem of Calculus is probably one of the most important theorems in all of calculus, in that it really builds the bridge between the two branches, differential and integral calculus. Every topic in math has its own fundamental theorem. There's a fundamental theorem of algebra, there's a fundamental theorem of arithmetic, and they all have something in common in that they are extremely important, but usually very easy to understand. And so here we have this fundamental theorem of calculus. So it says, if a function f is continuous on a closed interval from a to b, so that means that interval is a finite interval and the function is continuous the entire time, And capital F is the antiderivative of f on that interval, then if I wanted to do this definite integral, rather than do all that limit as n goes to infinity of the sum business that we just got done talking about, what it says is I can just do simply this. Find the antiderivative, which is f, and plug b into it, plug a into it, and take their difference. That's it. So if you think about that example I just gave you a second ago, and I did it really quick, but it was the integral of 2x dx from 0 to 1. And what I showed you was that if we look at this here, okay, it's really just this triangle, 0 to 1. And if I do it through summations, I mean, I can sit here and take a bunch of rectangles, I can add it up. But ultimately what I'm trying to do is find this area. And since I have geometry on my side, I could find that area with geometry, and we found out that that area is 1. So this integral we know equals 1. But what I can do is I can use what we talked about to do the indefinite integral, which is the integral of 2x dx equals x squared plus c. And so what I can do here is I can use this to get this answer. So what I'm going to do is I'm going to say, okay, the integral of 0 to 1 of 2x dx is a definite integral. What this tells me to do is to take the antiderivative, which is x squared plus c, and I'm going to plug in two numbers into that, 0 and 1. So I put the straight line on the end of it, and I'm going to plug 1 in first for x, which is, remember, because these are x values, these are on the x-axis. This is an interval as it relates to the x-axis. Okay, so I plug 1 in, okay, square it, plus c. Remember, c is just some random constant that we don't know. Minus, what happens when I plug this one in? This is my a. I find capital F of a, which would be 0 squared plus c. Right? Subtract those two from each other, and what do you get? 1 squared is 1 plus c, minus 0 squared plus c would be just c, so minus c, the c's cancel out, and I get 1. So the idea is that this fundamental theorem is the bridge between indefinite integrals and definite integrals. What it also allows us to do is to evaluate definite integrals without having to learn how to do the limit as n goes to infinity of the sum of f of c sub I delta x. Being that this is just an applied calc course and not a unified calc course, we don't really have to get into how we compute this. Okay? And ultimately because we can get the answer doing it this way. But I really would like you to understand what went into coming up with this formula. And that was the idea of adding up all those rectangles. Notice that the c's cancel out. And no matter what this function was, it would be something plus c. So I'd have something plus c minus something else plus c. Well, this is plus c and this is plus c and this one's being subtracted. That negative is always going to distribute, and this is going to turn into a minus c. So I'm going to have a plus c and a minus c. They're always going to cancel each other out. So when we get to the idea of using this fundamental theorem, we have to do a couple of things. We have to be able to find the antiderivative. Right? And so we need to make sure we can find the antiderivative of f, which we've practiced a lot of at this point. Right? Once we do that, we don't want to do the limit of the summation. Instead, what we can do is we can apply the fundamental theorem of calculus by saying, let's find the antiderivative. Let's look at the interval a and b. We'll plug b into the antiderivative, then we'll plug a into the antiderivative and take their difference. We don't have to use the constant of integration. If we had that plus c, this would have a plus c, this would have a plus c, and we just said that that would distribute and the c's would always cancel. So since the c's are always canceled, when we do definite integrals, there's no need for the plus c in any of this. So we're going to stop writing the plus c for definite integrals. For indefinite integrals, you still need your plus c. But since we know the c is going to cancel out, we're going to stop writing it. All right, so here's an example. If I said, let's do the integral from 0 to 1 of x squared plus 2x plus 1 dx. This now you have to recognize is a definite integral because of this. There's an interval here that we're integrating over. So I'm going to do the antiderivative, which would be x cubed over 3 plus x squared plus x, and evaluate it between 0 and 1. So that means I'm going to plug 1 in first, which would be 1/3 plus 1 plus 1 minus, I'm going to plug 0 in, which would be 0 over 3, which is 0, plus 0 squared, which is 0, plus 0, which is 0. So ultimately, my answer will be 1/3 plus 1 plus 1, because this is all 0. So 1/3 plus 1 plus 1, 1/3 plus 1 is 4/3. 4/3 plus another 1 would give me 7/3. So 7/3 is the answer for this. Quick note. Not every definite integral has to represent area. And that might seem contrary to what we've already talked about, but not every definite integral has to represent area. You can make definite integrals represent area, but they don't have to. And so the idea there is that thing I set up earlier, which is the idea of whether or not my function, this function here, is above the x-axis or below the x-axis, or maybe even partially above and below. And that idea there is that what this is doing is adding up a bunch of rectangles. That's what this is doing, is adding up an infinite amount of rectangles. Those rectangles can be above the x-axis. Those rectangles could be below the x-axis. Okay? If they're above, I would get a positive answer for my integral. If they're below, I would get a negative answer for the integral. But if I wanted it to represent area, I wouldn't be able to really look at it exactly like this. What I would have to do is what we talked about, is take every one of those y values and multiply it by a negative so that it flips it up. It's a little complicated for what we need right now, but just a note to make to yourself is that not every definite integral has to represent area, although they can. They don't have to. What you're doing is you're adding up a bunch of rectangles. Sometimes they're below the x-axis, sometimes they're above, sometimes they're both below and above, depending on how the function works. But this answer we're getting is the sum of infinitely many rectangles' areas added together. Okay, so here are two really simple definite integrals that we can do. So let's look at A first. In A, we have the integral from 1 to 2 of x squared minus 3 dx. First thing I'll do is find the antiderivative. This should be really easy. X cubed over 3 minus 3x. And now I'm going to evaluate it between 1 and 2. So I plug 2 in first, which will be 2 cubed over 3 minus 3 times 2. That's f of b. Minus, I'm going to plug 1 in, which would be 1 cubed over 3 minus 3 times 1. And then I just do that arithmetic, which should be the easiest part of all. So this will be 8/3 minus 6. This will be minus 1/3 plus 3, because this negative has to distribute. So 8/3 minus 1/3 gives me 7/3. Negative 6 plus 3 gives me negative 3. Multiply this by 3 over 3. So I'm going to get negative 2/3. And notice that that answer is negative. Okay, that's okay. This question didn't say use the integral to find the area. It just said evaluate the definite integral. Over here, okay, this integral, again, not hard at all if we know how to do antiderivatives. I'll write this as x to the 1/2. I simply use power rule, which would be x to the 3/2 times 2/3 between 1 and 4. So I have 2/3 times, I'll plug 4 in and plug 1 in. I pulled the 2/3 out just because it's computationally easier. 4 to the 3/2. 3/2 means square root third power. Square root of 4 is 2. 2 cubed is 8. Minus 1 to any power is 1. So that's going to give me 7 times 2/3 is 14/3. Now, just because this number is positive doesn't necessarily mean it's an area. It all depends on how this function looks graphically and how this function looks graphically. Let's look at the two of them. X squared minus 3. X squared minus 3 would be a parabola down 3 units and look like this. Okay? And it's going to hit the x-axis at square root of 3, which is roughly 1.7. And I'm doing the integral between 1, which would be over here, and 2, which would be over here. Well, if this is continuing to go up like that, x-axis is my bound. here's my one and here's my other. If I put this to the function, I'm basically finding these two areas added together. Now my picture isn't drawn to scale, but the idea is part of my function's below, part of my function's above, hence the reason why I didn't get a great answer in terms of a positive answer. Look at this one here. If I was to draw the square root of x, square root of x looks like that. Here's 1, here's 4. Everything about this is above the x-axis. That's the interval from 1 to 4. Here's the function. So this 14/3 is actually that area, okay? Because that area is above the x-axis. This negative 2/3 is not the computation of the area because of the way my picture sets up. But it doesn't matter. That's not what this question is asking you to do. This question is just saying evaluate the definite integral. Now that we have an idea of how to do a definite integral, the last thing we need to talk about with this is how to then incorporate substitution, which is change of variables. There's two ways to do it. To me, one is definitely going to be easier for you than the other, especially in this beginning stage. The easier way to do it would be to just keep doing what we've been doing all along with substitution, which is substitute your u, do the integral, then go back and resubstitute and turn back into x, and then we'll worry about the definite integral part. But there's another way to go about this. And the other way to go about this is to not resubstitute your u back in and just keep everything in terms of u. Now there's a small problem there. The problem there is that when we do this, these values right here, 0 and 1, are x values. This is an interval on the x-axis. And so these can only be plugged in for x's. If I switch over to u's and I want to plug something in for u, I would have to figure out what u equals. So I'll show you two ways to do this. One, I think, is the one that most people will end up doing. It's the first one, which is, all right, just forget about this 0 to 1 right now for a second. Let's just think we had to find the antiderivative of this. And so you got to use your concept of substitution to do that. And the concept of substitution is to realize that the derivative of this will somehow give me that value. So if I say, let's let u equal x squared plus 1, du is going to be 2x dx. But notice I don't have the 2. I have x dx left over. So I'll divide by the 2. And so what I have is I have this integral from 0 to 1 of u cubed du over 2. The over 2 I'll pull out as a 1/2. Now, do my integration to find the antiderivative. So this 1/2 is here. I'll add 1 to the power, divide by that new power, right? I'm not going to put plus c on the end of this because I know I'm going to do a definite integral. But then I have this. I have the 0 to 1. But remember, these are x values. And this is the problem. This is a u. I can't plug these in yet. What I have to do is what we would normally do, which is go back to x. Since u equals x squared plus 1, I'm going to say, okay, 1/8, because that's the 2 and the 4 multiplied together, times x squared plus 1 between 0 and 1. Now I can plug this in for x and subtract. So the idea that we always used to do when we did substitution last week was that we have to resubstitute back in. Well, that's the same thing here. So now I can plug the 1 in and the 0 in for x, and I would have 1/8 times, plug 1 in, you get 1 squared plus 1, minus plug 0 in, you get 0 squared plus 1. So ultimately what you see you end up with is 1/8. This will be 2 minus 1, which would be 1, so 1/8 is the answer. All right. No big deal. Like I said, I think that's the way most people will go. Resubstitute your x back in and then plug these definite values in. But there's an alternative. The alternative is to switch these over to u values. And then you could stop here and you can plug right into here. How do you do that? Your substitution. You have that u equals x squared plus 1. So if x equals 1, you could find that u equals 1 squared plus 1, which means u equals 2. If x equals 0, you can find out that u equals 0 squared plus 1, so u equals 1. So instead of x going from 0 to 1, right, we have u going from 1 to 2. And so here what I could do is I could have said, well, I have this 1/8 u to the 4th, okay? I see there's a mistake. There's a major mistake here in that I didn't bring the fourth down. Look at this mistake. There's a 4 that's supposed to be on here. This is u to the 4th, which u was x squared plus 1, so that's to the 4th. So this should be to the 4th in either case. Well, if this is 2 to the 4th, 2 to the 4th would be 16, and 1 to the 4th would be 1. So that would give me 15/8, not 1/8. That's a major mistake there, but easy to fix, okay? So back to this problem here. So now what we can do is we can go, okay, well, I have 1/8 u to the 4th. U is between 1 and 2. So now that I have the u between 1 and 2, and these are u values, I can plug them right in here without having to turn this back into x, which you see will ultimately give me the same thing, because I'll have 1/8 times 2 to the 4th minus 1 to the 4th, which is what I just did here, and you saw that was kind of my mistake. I missed the 4th power here. And I would still get 16 minus 1, which would be 15/8. I don't think I like doing it this way as much. I think students don't like doing this way as much because you're so used to your basic rules of substitution, where you go to u and then you go back to x. But either way, it works. Right? You decide what works best for you. So if we do this integral, this is a definite integral. What I'm going to do is try and figure out first, how do I find the antiderivative? This is a pretty involved question, so it looks like u substitution might be the best bet. If I say u equals 2x minus 1, the derivative is going to be 2 dx. I have this dx here, but I don't have a 2, so I can divide that out. But I still have this extra x here as well, which we've seen this before. If I take this and write this as u plus 1 over 2 equals x, so just add the 1, divide by 2, I know what x equals in terms of u, so now I can get that x out and put u's in its place. So I have 1 to 5, that's just going to sit there for a second. I have u plus 1 over 2 divided by, this will be the square root of u, and this is du over 2. So this is the x, this was the square root of u, and this was the dx. Okay. Simplify this a little bit. This over 2 can come out as a 1/4. I have u plus 1 over the square root of u du. Let's now figure out how do I do the antiderivative. What I'm going to do is a trick that we've learned a bunch of times. Split this up. So I get 1/4 integral from 1 to 5 of u over the square root of u, since they're being divided and they have the same base. I subtract the powers, that'll be u to the 1/2. And then this 1 over u is u to the minus 1/2. Sorry, 1 over square root of u will be u to the minus 1/2. du, now I can use power rule. So I have 1/4, this will be u to the 3/2 times 2/3, minus this will be u to the 1/2 times 2. Now, here's I got 1 to 5. Now, I could choose to change this 1 to 5 to u values and then just leave this as is, or I can choose to turn these back into x's and leave these as is. Completely up to you. In this case, I have to plug u equals 2x minus 1 in here, and then plug the 5 into that. What I'm going to choose to do instead is to switch these to u values. So u equals, and what u equals. Why? Because it's very easy to do. Look, if x equals 5, u equals 2 times 5 minus 1, which is 9. That's just using this. If x equals 1, then u equals 2 times 1 minus 1, which would be 1. So now my u goes from 1 to 9. And now I don't have to do anything. I just plug 9 in, I plug 1 in, and I'm done. So if I do that, I have this 1/4. I have 2/3 times 9 to the 3/2 minus 2 times 9 to the 1/2 minus 1/4 times 2/3 times 1 to the 3/2 minus 1 to the, or 2 times 1 to the 1/2. Okay? So 1/4 times 9 to the 3/2. That's the square root of 9, which is 3. Then cubed is 27. 2 times 27 would give me, what, 54 over 3? Minus square root of 9 is 3, times 2 is 6. Okay. Minus 1/4 times anything, 1 to any power is 1, so this will be 2/3 minus 2. But 54 divided by 3, that is 18. And so this will be 1/4 times 18 minus 6 would give me 12. Minus 1/4 times 2/3 minus 2. Well, 2 is 6/3, so that'll be what? Minus 4/3. Pull the 1/4 out. Thirds would give me 32/3. Cancel the 4. So I end up with 8/3. And all that's just basic arithmetic. But the idea is this is a definite integral with substitution involved. I chose to go this way with the substitution and to change these to u's as opposed to plugging in 2x minus 1 in. Okay, now let's circle back to the question we started off with, which is, let's try and find the area bounded by the curve y equals 1 minus x squared between 0 and 1 and the x-axis. So it was this space in here. Find the area of that space. So what we can do, since that whole function is above the x-axis, okay, we could take the integral from 0 to 1 of 1 minus x squared dx. And that will give us the area. This is our heights. Our heights is based off of this function. That's the function in here. The width is 0 to 1. That's here. Okay? And so we get what? Well, this 1 minus x squared dx, if you look at this, we have to do the antiderivative of 1, which would be x, and x squared would be x cubed over 3 between 0 and 1. We'll plug in 1. We'll plug in 0. Subtract them, and I end up getting, well, this is just 0. I end up 1 minus 1/3, which will be 2/3. So this area in here, even though one of the sides of this area is a curved side based off of this function, that area can be computed very simply as 2/3. Again, based off the fact that my function is above the x-axis, this is very easy to do. Anytime your function is above the x-axis, okay, and you have some interval on the x-axis, and you want to find the area bounded there by the x-axis, you could simply do that by the integral from a to b of f of x dx. And we now know how to compute this using antiderivatives and the fundamental theorem. But that's how we compute an area when we have any one of these sides being a curved side.